Imagine this. You're hired as a physics-inspired data scientist at a fast-moving tech company. Your specialty is blending physical intuition with machine learning fundamentals, and the company loves you for it. One of the core parts of their business relies on generating handwritten-style images, thousands of them every day. And for that, they use ChatGPT's image generation tool. It has always worked flawlessly. Until today. You try to send a test request to ChatGPT's servers and nothing comes back. The servers are down. Completely. Within minutes, your boss storms into your office with a look of pure panic. The company has a major deadline today with contracts on the line, and the entire workflow has stopped because those synthesized images can't be generated. Your boss leans in and says, "We need an alternative. Build something. Anything. You're the physics AI guy, so fix this." You look at him like he must be joking. Build an image generator? In one day? On a laptop? You think about what it actually takes to train a model like the ones used inside ChatGPT. Months of engineering, massive GPU clusters, billions of dollars in research pipelines. And here you are, sitting with a laptop and a crisis looming over your head. But after the shock settles, a thought hits you. Maybe you don't need a billion-dollar model for this specific task of generating handwritten-style images. Maybe you just need fundamentals, the core physics-inspired idea behind such generative models. And if you can strip the concept down to its mathematical roots, maybe you can build something small and simple, but functional that avoids deep learning entirely. If you want to know how this story ends, and how you can build such a model yourself, stay tuned. And by the way, the model we described today is implemented in a Python script. You can find it in the description below and generate a few images yourself. And if you're curious about exploring real scientific research in this area, I'll share a couple of raw and exciting research ideas at the end. Did you know that every machine learning model, from simple regression to image-generating models like DALL-E, can be explained by a single elegant equation? If you're interested in learning machine learning in a unified way, visit our webpage at compuflare.com. This is a unique place to understand every machine learning model through one elegant equation from a physics-inspired perspective. In addition to the courses, we offer end-to-end intermediate and advanced projects that develop your skills, experience, and online presence, helping you land top industry roles. Visit compuflare.com and start building your data science career. Now let's talk about the core concept underlying image generators. As a physics-inspired data scientist, you understand the deep fundamentals of generative AI. You've studied diffusion models that are behind modern image generators. And you know something crucial. Despite their complexity, the mathematical backbone is surprisingly simple. The main idea is that diffusion models learn the probability distribution of images from data. In physics language, the pixels of an image is represented by a vector x, and we aim to express the probability of that vector in the following form. The image generators don't dream images. They simply synthesize new vectors that are highly likely according to the estimated probability distribution. So, if you know the probability p, even an approximate version of it, you can generate new images. Your idea is simple. Skip the deep learning machinery and the huge compute that takes months-long training. Stick to the fundamentals and somehow estimate p directly using classical machine learning tools that run on a laptop. But how? This is when you remember a classical approach from machine learning grounded in simple math, the kernel density estimator. It's a tool specifically made for constructing a probability distribution from data points. If you've taken physics or engineering courses, you've seen this before under many names. Fourier transforms, Legendre expansions, spherical harmonics. They all follow the same idea. Take a complicated function and expand it in terms of simpler basis functions, expressed as the following. The phi of x are basis functions, and the coefficients tell you how much each basis contributes. But usually you compute the coefficients through integrals or derivatives involving p. And that itself is the first problem. You don't know p. So instead of abandoning the idea, the kernel density estimator modifies it. It renames the basis function phi to a kernel centered at each data point, expressed as the following. And instead of computing weights using integrals, it sets them directly based on the data. To understand this intuitively, imagine a beehive. Suppose you want to estimate the probability of finding a bee at some location X. How likely are you to find a bee far from the hive? Almost zero, simply because you've never seen bees out there. The observed bees, the data points, define where probability should be high or low. Your probability estimate should depend on how many bees you've seen near location X and how close they are. So you can simply write the probability as a sum over the observed bees, which are the data points in this example, in the following form. To account for low probability far from the beehive, the kernel must be a function that decreases with distance from data points, and a natural and common choice is a Gaussian kernel, expressed as follows. This ensures that data points contribute strongly near themselves when the distance is nearly zero, but weakly far away. To account for the fact that a region with higher number of bees should be more probable than a region with fewer number of bees, every data point should contribute to the overall probability with equal weights. That means the weight of each bee is simply 1 over the number of all the observed bees. Finally, you scale distances by a bandwidth h so that distances become dimensionless, expressed as the following. The parameter h acts like the resolution power of the model. Ideally, you want it to be close to 0 and get the highest resolution. But that requires infinite number of data points. Practically, you want to set h as small as the number of data points in the training data allows you. You can think of h as how spread out each bee's influence is. Large h means every data point influences a wide region. Small h means influence is tightly localized. We usually treat h as a hyperparameter. We inspect various values and see which one gives a better score. Now the question is, can this idea generate the images that your company need? You know that an image is nothing but a vector, whose pixels are the components of the vector. So the probability distribution of an image can be estimated by a sum over the images in your training dataset, expressed as the following. And speaking of datasets, you remember a small-size dataset called MNIST that only contains images of handwritten digits. Its small size ensures that you can avoid GPU clusters and simply stick to your laptop for computation. Also, it has exactly the kind of handwritten digits your company needs. In other words, you will be learning the probability distribution of handwritten images and not, for example, the probability distribution of images of horses. But now you face a major issue. Kernel density estimation, or KDE for short, works beautifully in low-dimensional spaces. In the B example, the vector x was just physical position with 3 dimensions. MNIST images have 28 by 28 pixels, so each one is represented as a 784-dimensional vector. KDE in such high dimensions collapses, something we call the curse of dimensionality. This is exactly why modern image generators use neural network machinery and advance ideas to approximate P. But you don't have that option. So you do what any good scientist does. Change coordinates to reduce dimensions. You turn to principal component analysis, or PCA for short. The idea is simple. It's like describing the surface of a sphere. You could use XYZ coordinates and end up with 3 dimensions, or you could work in the spherical coordinate system where you only need 2 angles, phi and theta, and end up with 2 dimensions. We will cover PCA in another video. For now, simply think of it as a method that exploits symmetry and compresses the information from 784 dimensions down to, for example, 50. Now you have everything you need. A classical machine learning estimator for probability P, a small-sized dataset containing the subject you are interested in, a way to reduce dimensions of the images, and a laptop. You write the Python code to load the MNIST images, apply PCA, train the KDE to estimate the probability field of the entire space of handwritten digits. Then you start synthesizing new images from the estimated probability. This is called sampling. The simplest way to understand sampling is this. Propose many random candidate vectors, compute their probability using your estimated version, and accept or reject them based on how likely they are. In practice, There are more advanced sampling techniques that we will cover in future videos, but the fundamental idea is what I just described. After a few tries, something magical happens. Your code begins generating new digits. They're not copies. They're genuine new digits that look like they could have been written by a human, but that never existed before. Now you've built an image generator on a laptop in a few hours using nothing more than classical machine learning tools and physics-inspired thinking. Your company is saved. Before we wrap up, here's a research-level idea that I can think of at this time. In earlier videos, we discussed how first principles suggest an exponential form for the probability of a dataset, expressed as the following. The exponential form of the probability means that it varies very rapidly from a region represented by vector x sub 1 to another region represented by vector x sub 2. This variation can lead to significant reduction in the quality of our estimate. So, instead of estimating P directly, we can try estimating the effective free energy landscape F. Because F is logarithmic, it's inherently more stable than P. And given that Z is just a constant, once we find F, we actually have the unnormalized probability with actual predicting power. We can also take it a step further and find a physics system dual to the machine learning problem at hand and expand F in the basis functions of that space. This connects our machine learning problem to a physical system with deep mathematical structure. It gives us interpretability and the chance to uncover new principles behind generative models. If such research ideas excites you, consider joining our community. Create a free account on our website and get notified about future live events exploring exactly these kinds of fascinating connections. Thank you for watching, and I'll see you in the next video.